Hi everybody, welcome to EE3003 Tutorial 2. Let's take a look at the question 1. This problem has given us two loan conditions. The first is the settings. As you can see, this is an inverter problem, so we can draw the inverter like this. As you can see on the picture. And the second condition is that we are given the parameters of the moles. Therefore, we can calculate the K according to this formula and calculate the Kn, Kp, and also the Kr. Now, in question 1a, we need to calculate the noise margin. So, what is noise margin? For an ideal inverter, you can see that when Vin increases from 0 to high voltage, Vout will suddenly decrease to 0. But for a real inverter, it will take some time for Vout to follow, and it will decrease in some time to 0. And on the graph, you can see the amount of voltage we need to calculate is the noise margin for both low and high. So let's start to calculate the noise margin. Here you can see the formula for noise margin, both high and low. And usually the VOH will be the VDD, the highest voltage, and the VOL will just be 0 volt, the ground voltage. And so the real value we need to calculate in order to derive the noise margin is the VIH and VIL. In order to calculate these two values, the nodes has done an extensive calculation to derive this formula for these two variables. Here I just list the formula for these two variables. Even though these two formulas are called the formula to calculate the two values, but actually it cannot directly derive the values for VIH and VIL. That's because in each formula there is another variable that is unknown, which is Vout, as specified by the dotted box. In order to solve the VIL and VIH, we need another formula, which is the current equation. And it's the current in the PMOS and current in the NMOS. They should be equal because they are on the same line. And ironically, this equation is also used in the nodes to derive the above formula for VIL and VIH. So please don't be confused that we are going to use the current equation again together with the VIL and VIH formula, even though the current equation is used to derive those two formulas in the nodes. And of course, the current equation in the PMOS or NMOS, the current equation you can find in the nodes for either the PMOS and NMOS in linear region or in saturation region. And you can combine these two formulas, the current equation and the VIL or VIH formula, to derive the VIL, VIH values. Let's start the calculation for VIL. First of all, we adapt the formula from previous slides. So you can see the formula in the second row. And then we plug in the values we know, except for the Vout. And then we can derive a relationship between Vout and VIL, as shown in the dotted box. As you can see, this formula alone cannot solve the problem, because we have two variables unknown. Therefore, we need another equation, and we can look for that in the current equation. In order to derive the current equations, we need to know the state for the NMOS and PMOS. And this is something that you really can memorize and refer to the nodes. There are different regions for the inverter, and in the VIL region, the NMOS is in saturation and the PMOS is in linear region. Here we have listed the current equation. On the left-hand side, it is for NMOS in saturation, and on the right hand side it is PMOS in linear region. And before we can solve this equation, that we need to do a little calculation. And as you can see from the right hand side and associate with the inverter graph, we can easily derive the values for VGSN, VGSP, and VDSP. Finally, we plug in all the values we have derived, and also replace V out with the formula we have derived previously in the dotted box, and we can get this quadratic equation, and we can easily solve that and find out VIL to be 1.198 volt.